A Latin square arranges numbers, letters, or symbols in a square grid so that each appears exactly once in each column and once in each row. Shown here is a 4x4 Latin square where every row and every column has red, blue, orange, and green exactly once each. Latin squares are used when conducting experiments where there are 3 different factors and each has the same number of levels. Often it would be impossible to test every possible combination in this situation. However, using a Latin square design, you can conduct an analysis based off a much smaller number of observations, while keeping the effect of uncontrolled variables small. Fewer samples are needed this way than using random sampling. The levels of one factor are represented by the columns, the levels of the second are represented by the rows, and the third by the symbols within the Latin square, in this case colors. Often factor 1 and factor 2 are not actually being analyzed and you are just controlling for their variation, while factor 3 is the treatment you are actually testing. One example of using a Latin square for an experiment in engineering is in the design of an ultrasonic aircraft. The volume of sonic booms needs to be minimized as much as possible. To do that, you could test different configurations of the plane, such as different wing designs, tail designs, and engine placements. It would take too many resources to test every single combination. A Latin square design can be used instead. In this example, there are 4 wing designs, 4 tail designs, and 4 engine placements under consideration. Columns represent the wing designs, rows the tail designs, and the engine placements 1 to 4 have been placed so that each is tested once with each wing design and once with each tail design. The observed boom volume for each combination has been recorded in the Latin square. To analyze the Latin square, start by summing each row and each column, and then summing each level of factor 3, the engine placement. The engine placements have been color-coded to make it easier to see. When you total the sums of rows, the sums of columns, and the sums of engine placements, all 3 should be the same number, in this case 1564 decibels. Then you can use ANOVA to analyze each factor. For each, calculate the sum of squares, mean squared, degrees of freedom, and F ratio. Comparing the p-values to alpha, the engine placement and wing design are both significant, while tail design had no significant effect at all. Looking at the wing design and engine placement totals, it seems obvious that the wing design A and engine placement 1 by far result in the smallest sonic booms, and this can be confirmed by other statistical analysis techniques.